Now it's recording. So whoever is going to watch the video, this is going to be a bit slow paced. So we're going to start off with the most basic question 28. We'll just do a couple of parts. So I'll start off with the first one. We want to find out the probability that the standard normal variable z takes on values between 0 and 2 points.
So your screen isn't visible. It's visible now, sir.
Okay. So again, this function that we've just and a circle with a bar crossing it is used for denoting the cumulative standard normal. So this problem turns out to be this one. Okay, then we'll take a look in our standard normal table. So the table on page A7, 2.1, the row labeled 2.1 and the column labeled 0.07. The intersection of that is this cell 0.9850. Okay, for 0 we don't even need to look at the table. This is 0.5 and the required probability comes out to be 0.4850. Okay, basic stuff. Now after this, let's straight away jump to part J of question 28, which is modulus of z is less than 2.5. This can be written as z taking on values between minus 2.5 and plus 2.5. We'll transform this into a problem involving cumulative standard normal. So this again, the probability that the standard normal variable takes values less than 2.5. This is 0.9938, and the probability that the standard normal variable takes values less than minus 2.5, that is 0.0062. So we have 0.9876. I'm going to draw a diagram as well so that there's no doubt in anyone's mind. This is minus 2.5. Standard normal is centered on 0. This is plus 2.5. This is what we want. Okay, so what we've done is we have taken the probability that the value standard normal variable takes values less than 2.5. So all the area to the left of 2.5, and we've subtracted from it area to the left of minus 2.5, and we get the required area. Okay, any problems with these two? Otherwise, I'm going to move to question 29, which is again quite basic. Please read question 29. Please mute yourself. Someone is unmuted. This disturbance is going to get into the recording. Okay, so what we need is we're given expressions involving an unknown c, and we need to find the value of c from that. So the first one is given as is 0.9838. Okay, so all you need to do is locate 0.9838 in the table, and then from that get the value of c. Okay, let's see where that is. 0.9838. Yep, so this is in the intersection of the row labeled 2.1 and the column labeled 0.04. So 2.1 plus 0.04, C turns out to be 2.14. Okay, take a look yourself, it should be clear. Let's look at part B. Now we want this probability that the standard normal variable takes on values between 0 and C. This is given to be 0.291. Okay, so just by reading this, I can see that C is non-negative. In fact, it's positive because the probability that standard normal takes values between 0 to C is non-negative. So we have C somewhere over here. This is what we want. This is what we're given, 0.291, and C is what we want. We can transform this problem this way. So what we're doing is probability Z less than equal to C is area under the curve to the left of C, and from that we're subtracting -5. This area is minus 0.5. So this becomes 0.291 plus 0.5, so it's 0.791. And now we can just look at the table and look for this value 0.791, which is at the intersection of the row labeled 0.8 and the column labeled 0.1, 0.01. This is 0.81. Okay, any problem with these? There's no problem. Then we're going to move to the third basic one. We need to find the percentile for standard normal. I'm just going to do part A. We need 91st percentile for Z. Okay, now just look at the table and find me the 91st percentile for Z. Get me the value of C. Yes. So all we have to do is look for 0.91, and what we get is we don't exactly have 0.91, we have 0.9099, which is good enough. So C is approximately 1.34 because this 0.9099 is at the intersection of row labeled 1.3 and the column labeled 0.04. So we have 1.3 plus 1.34. Okay, no problems with these. Okay, so we're through the basic ones. Now, which one should we do? I'm going to pick up problems randomly. So let's move to question 39. It's the same in the PDF and your readings. Please read question 39. So we're given a normal random variable. We'll use the usual notation x. And this normal random variable is parameters 30 and 5. So x follows normal with parameters 30 and 5. We need 91st percentile. Okay, so we'll start with 91st percentile for the standard normal. Get me this 91st percentile for the standard normal. Okay, we'll do step by step. So this is something we just got, 1.34, and then we'll transform this into 91st percentile for x. Okay, so we have this expression right here. X is equal to mu plus z into standard deviation. So mu is 30, z we figured out is 1.34, and standard deviation is 5. So this comes out to be 36.7. Okay, so what I'll do is I'll do questions of my choice first, which is according to uh, the level, and then I will do every question that you want me to do. Okay. If I don't do it in the class, I'll give you the solution or I'll do it in the next class. But no question will be left untouched that you ask me to do. Okay. Any problem with 39? Okay. Now read question 45 after this. It's the same question in the PDF and the text. Starts with a machine that produces ball bearings. So what we're given a random variable x, which is diameter of a randomly selected bearing. And we're told that x follows normal distribution with parameters 0.499 and standard deviation point 002. Okay, and we want the percentage of bearings that will not be acceptable that are produced by the machine. So probability bearing not acceptable. This is if the bearing is different from the given true average diameter 0.5 by 0.004 inches. So this is if x minus 0.5 is greater than 0.004. Okay, is this clear? This description? All right, no response will be taken as no issues. Okay, so this is 1 minus p into x minus 5 less than equal to 0.004, 1 minus p into minus 0.004 less than or equal to x minus 0.5 plus 0.004. Now let's standardize this. So minus 0.004 plus 0.499 divided 0.002 z. So we'll have minus 1.5, 2.5, 1 minus, okay, this will come out to be 0.073. So we can say that 7.3% of bearings will be unacceptable. Okay, so this question brings out the use of normal distribution in industry very nicely. Okay, after this, please read question 48. Okay, so there is a conceptual issue involved. What we're being asked is if we're given the standard normal table with only positive values of the standard normal variable. Okay, that is if you're only given the portion that is on page A7. How can we figure out the problems that are given to us? Just part A. How can we calculate probability 1.72, probability that the standard normal variable takes values between minus 1.72 and minus 0.55. Okay, this is our standard normal curve centered on 0. What we're being asked is to calculate the shaded area, which will be exactly the same as the shaded area between values 0.55 and 1.72. So we can say that by symmetry, normal distributions are perfectly symmetrical. We can transform this problem into this one. Okay. And then just look at the portion of the standard normal table which only has positive values of the standard normal variable. Okay, let's look at part B. Now we're being asked, how do we figure this out? All right, so one, either we can look at, let's look at the problem first in the diagram. Centered at 0. What we want is this area. Okay, now the green shaded area is same because of symmetry. So area from minus 1.72 to 0 is the same as area from 0 to 1.72. Okay, so we can break this problem into this one: probability that the standard normal variable takes on values between 0 and 1.72, which is the green shaded area towards the right of 0, and probability that the standard normal variable takes on the values between 0 and 0.55, which is the blue shaded area. Okay, so we're now to the right of 0. Should not be a problem. Okay, any issues with this? All right. Next, let's look at question number 50. Please read 50. It starts with, in response to concern about nutritional content of fast foods, McDonald's has announced. All right. So what do we have? We have a random variable given to us. Let's denote this with x. This is number of people in 1000 who can taste the difference. Okay, so this random variable follows binomial distribution with sample size 1000, and the probability of success for the random variable as we've defined is 3%, because the company is claiming that 95% can't detect the difference, so 3% can. 0.03 is the probability of success. Now let's see what these values are. N into P, N is 1000, N and P probability of success 0.03. This is 30, which is greater than 10, and N into 1 minus P is 1000 into 0.97, which is 970, again something that is greater than 10. So according to the rule of thumb that we have, we can approximate this binomial distribution with normal distribution. Okay, so I can say that x approximately follows normal distribution with parameters mean, which is n into p for binomial. We'll use the same mean. This is 30, and the standard deviation, which will be 1000 into 0.3 into 0.97. This will be 5.394. Okay, so mean and standard deviation will just pick up from the binomial distribution. 0.394. All right, now what do what are we supposed to do? We're supposed to find out in part A. That that is what I've done. NPQ. If P is 0.03, what is Q? It's 0.97, right? Okay, this is 0.03. I think this was the confusion. Fine. Typo. This will come out to be 5 point. Okay, so it was just a typo, no problem. So we need to figure out at least 40 can take the difference. The probability that at least 40 can take the difference Okay, so we need a random variable to be greater than or equal to 40. So straight away do this. Okay, now usual confusions. X is still a discrete variable. We're just approximating this with normal. So these inequalities and equality sign, they matter. Okay. Now, because we're using a continuous distribution to approximate a discrete distribution, we'll have to make continuity correction. So I'll just okay, this will happen. So let's say this is 40 and we're using normal distribution. We want the area to the left of this point, 40.5 under our normal curve. Okay, so okay, no, we don't want this. We want the probability that this is less than 40. So we don't want the area of the rectangle just above 40. We want area to the left of this value, 39.5. So this is the correct way of writing it. Now we'll standardize this in the same bracket. So 1 minus cumulative probability with value 1.76. This will be 1 minus 0.9608 0.0392. So approximately 3.9% of the people, the probability that at least 40 can taste the difference between these two oils is 0.039 approx. Any problem with this?
So,
Yes.
so can you please explain some correction factor once again?
Okay. Let's use colors. So probability that the random variable, the discrete random variable x takes on value less than 40 is the probability of all these shaded triangles, shaded rectangles. Is this fine? We don't want 40. We want, if this helps, let me write an intermediate step. 1 minus probability x less than equal to 39. Is this fine till here?
Yes, sir.
Okay. Now, in the bottom panel, what we're doing is we're using continuous for approximation. So this value, okay, this one is 39. we want this area. So just look at the correspondence between, wait. We want this one as well. We don't want the area of the rectangle centered on 40. We want the areas of the rectangle centered on 39, 38, all the way to the left. So this is the correspondence between the two diagrams. Now what I want is, I want this value which separates the rectangles based on 39 and 40. It's in the middle because the width of every rectangle is 1. So that's what I have. Let me make it more clear. This is 40. This in the middle is 39. So this value is 39.5. Is this okay now? Tell me.
Yes, sir. Thank you.
Okay. Let's read part B. So we want the probability that at most 5% can taste difference between the two oils. So we want the random variable x to be less than or equal to 5% of 1000, which is 50. Okay, so this is straightforward. We make the continuity correction because we want the area of the triangle centered on 50 to be included. We just move our point to the right by 0.5. So I'm doing both the continuity correction and standardization in the single step. Okay, this is 3.8. Now our standard normal table is just given till 3.4, and we see that approximately the area under the curve till 3.4 is 1, is 0.9998. So we can confidently claim that this area is approximately 1, as good as 1. Is this point clear? So table is given till 3.4. So this area till 3.4 is 0.9998. What we want is area under the curve till a value which is further away, 0.3, 3.8. So it's even greater than 0.9998, which is as good as 1. All right. Any problem with this? Okay. Now I'll ask a question that you will do for me. The similar question, just to be sure that you know the stuff. Read question 52. Okay, so what we're given in 52 is a random variable x, which is number of flaws along a 100-meter reel of magnetic tape. Okay, now the number of flaws obviously are going to be integer values. So x here is a discrete random variable. Now, we're not given any such information what probability distribution the x follows exactly. We're just given that x approximately follows normal distribution with mean 25 and standard deviation 5. That's enough for us. Okay. Now, whatever distribution x may exactly follow, we're going to have a histogram like this. Okay, so x here and probability of x on the vertical axis. This is the exact probability distribution, so I'm going to write p of x with black. I'm writing this in blue as the blue curve is density, so that's why I've written f of x in blue. Is what we're doing. Now get me the solution for part A, which is the probability that the random variable x takes on values between 20 and 30 inclusive. That means we use less than or equal to sign. Okay, do your calculations, do continuity correction, get me the answer. Whoever is watching this recording will probably have to fast forward tits and bits. I'll wait for a few minutes. That is correct. 0.7286 is correct. Anyone wants me to do this problem? Okay. So let's see what we have. Mean is 25. So because the mean of the distribution is given to be 25 and the standard normal will be centered on 25. Let's say this value is 30 and dot 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 dot. This value is 20. So I've put in dot 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 just to claim that this is not exactly there should be more rectangles. I don't have that many. Okay. What do we want? We want the area of all these rectangles combined. Okay. In terms of area under the normal curve, I want this value and I want this value. Area between. Okay. Let's break this up first. So any problem with this step? This is a basic step that we've been doing all along. Yeah, so probability that a random variable takes on between 20 and 30 is the same as probability that the random variable takes all the values less than or equal to 30 minus probability that the random variable takes all the values less than or equal to 20. Now we'll use the continuous distribution. So this point here to the right of 30 by 0.5, this is where we're making continuity correction and standardizing in the same step. So 30 plus 0.5 minus 25 by 5. Yeah, so this 0.5 is for continuity correction. Again 20. Okay, so either you can say 20 minus 0.5 because we want this point to the left, which is 19.5. So both would work. Either you can write 20 minus 0.5 or you can write 19 plus 0.5. Minus 25 by 5. What we have is then 1.1 minus again minus 1.1. Okay. Now this will come out to be 0.7286. Okay, so you might have to look at the table again. Any problem with this now? These calculations, you just have to look at the table and find values. Should not be a problem. Now tell me conceptually if this is fine. Again, no response will be taken as no problem. Okay, so the request was for question 47, 46B, and 49D. I think with the ones that I have done, you should revisit all three and you should be able to do all three with this. Okay, tell me if there's a problem. I'll sort them out myself. Now let's proceed to which one should we do now? '57. Please read 57. So what we're asked to do in 57 is prove that a linear transformation of a normal distribution also follows normal distribution. Or in other words, if you have a normal random variable, a linear transformation of that normal random variable is also a normal random variable. So in terms of notations, we're given a random variable x, which follows normal distribution with parameters mu and sigma, and we're given another random variable, which is a linear transformation of x. We need to show that y also follows normal distribution. Will fill in the parameters towards the end. Let's start. So I'll use the following notation: f with the subscript y of y. This is to denote the cumulative distribution function of y. Smaller case f of y. This is the density function of y. So CDF of y, PDF of y, CDF of x, and PDF of X. Now, what I'll do is I will take Chebyshev's inequality questions in all the exercise. We have a couple. I have made a note of that. We have a couple of questions from earlier exercise. I'll do Chebyshev inequality in one series for all the exercises. Is that fine? Okay. So for a equal to 0, that means we have a linear transformation on the positive side. Okay, so this is the usual notation. Probability that the random variable y takes on a particular value denoted by smaller y is can be denoted as the value of the cumulative distribution function of the random variable y evaluated at any particular value denoted here by small case y. So now we substitute y with ax plus b, which is in the linear, because y is the linear transformation of x. So what do? We subtract b and divide this by a, because we're taking this for positive value, so the inequality sign remains as it is. So we'll have y minus b divided by a. Okay, now this description can be written as, okay, so this is probability that the random variable x takes on value less than this particular value y minus b by a. So this is the same as the CDF of x evaluated at the same value. Okay, so this is, we have this result. Now what do? Let's just differentiate both sides. No, let's differentiate this d by dy. What are we going to get? This will be, okay, so differentiating the CDF gets us the PDF. But that would be, this would be d by dy into, okay, so we're using this result that we have derived. Okay, then the usual chain rule. So this would be 1 by a. Okay, tell me if there's a problem in this portion. what we wanted was a relationship between PDF of y and PDF of x. Okay. Now we already know that, let me just write here, that x follows normal distribution. So we know we can write the PDF of x as this 2 pi into sigma e raised to power minus x minus mu square divided by 2 sigma square. Okay, so f of x for this is, since x follows normal with parameters q, mu and sigma, I just make this substitution into e raised to power minus of y minus b by a minus mu square by 2 sigma square. So all I have done is I have replaced y minus b by a for the value of x, which was here. So x being replaced by y minus b by a. This is what I've done. Okay. Now on top of this, what I'm doing is I'm multiplying both sides by 1 by a. Alright. So on the left now, what I have, this is the expression for PDF of y. We have this from here. And to the right, we'll sort it out. This is 1 by root 2 pi multiplied by into sigma into e raised to power minus y minus b minus a into mu by a whole square divided by 2 sigma square. So we can write this as y minus b plus a into mu whole square, and this a square gets to the bottom and we have a sigma square. Fine. Okay, any issues with these steps? Okay, now let's see what we have got. This is a PDF of a normal distribution. Okay. With mean b plus a into mu and standard deviation a into sigma. Yes, whatever we have y minus, okay, this thing that I've highlighted in orange, that is the mean. And whatever we have here in the denominator highlighted with orange, that is the standard deviation. No problem. Okay. That means what have we proved with this? That y follows normal distribution with parameters a into mu plus b and a into sigma. Okay, so I said I'm going to fill it in the last. This is what I filled at the bottom. Y follows normal distribution. All right, any problem with this now? Okay, so there were two requests today. One was for series of questions 46B, 47, 49D. I believe with what we have done today, these three should not be a problem. Just attempt them again. And another one was for question 51, which relates to Chebyshev's inequality. And I also have two questions which are the requests have been made previously for questions for Chebyshev's inequality. We're going to get a couple more questions of Chebyshev inequality in one session. I'm going to do all of them together, so that will be better. All right, so let me stop recording now.